I'm very honored to be here giving the talk at the King's Factor lecture talk, and also happier that you guys decided to come and spend your afternoon with me rather than going and enjoy the sunshine. Yeah, so today I'm going to, as the title suggests, I'm going to tell you a bit about the what I think is the fascinating world of prime numbers. And I think, so a good math talk must always start with a joke. So what happened to the math teacher's garden? Does anyone know what happened? You might have come across this one. Anyone? Yeah, I heard some people. It grew square root. So, yeah, we are going to be talking a bit about square root today. So, because we're going to be talking about equations and things like that. Yeah, so as I said earlier, basically what I want to convince you is that numbers, especially prime numbers, they are very fascinating object. And maybe what you might suspect less is that they are kind of things that are in your daily life, whether you like it or not, right? So before we go any further, what I'm going to do is that I'm going to start with some basic stuff. I think I want to call this some kind of revision. And what I should have done a bit earlier is that, Alex did a very good presentation. So her slides were very well presented, very slick. And unfortunately, mine might be a bit boring in that sense. So, but I'm going to start with stuff that I think most of you have probably seen, even though they probably didn't call it arithmetic. So let's start with an example, which is an example of Euclidean division, right? So I think sometimes people call it long division. And so in this case, I want to start by looking at the division of 93 by 33, right? And I think what you've learned in high school is that this is how you write stuff. So you write your dividend here, the divisor here, and then the quotient here. And then you perform your division, and the remainder will be at the bottom. So it's kind of funny because, I kind of struggled for a while to get used to this, because when I did when I was doing my elementary study, I was doing it in a school where we did it in the French way. So in the French system, it's the other way around. So you would put it would be like this. I put 93 here, and then I put 33 here, and then so for a while, I don't know. For some reason, if you go to a different place, it's completely different. But anyway, so that's a minor thing. So if you perform this division, then you would get that your remainder is 27. The quotient is 2. And so you can write 93 as 2 times 36 plus 27, right? And what we learn is that you can make this. This is true for basically any two integers that you are given. So I'm using the word theorem here. I don't know if you're familiar with theorem, but if you are not familiar with the word theorem, you can assume that it's a statement that we can prove by a succession of logical statements. And at least, so let's pretend for the next 30 minutes or 40 minutes that you are university student. I'm just kidding. You'd see most of the stuff is quite accessible. So what Euclid theorem says is that this example that we just saw, it's a principle which is true for any number. So what does this mean? It means that if I give myself two whole numbers, a and b, and then I assume that b is positive, the statement is that you can find two numbers q and r, and I'm using those names to be very suggestive, quotient and remainder. So, and then the condition on the remainder that it's between 0 and b minus 1. And then you can write a as q times b plus r. So again, we saw this terminology before. So Euclid said that this, what we saw in this example is something which is true for every integer, whole number. Right. And as a consequence of this statement, of course, we have the notion of an integer being divided by another integer. So if I give myself two integers, and here again, it's important that those two, one of those integers is at least non-zero. In this case, we want it to be positive. And so we are going to say that b divide a, which is the same as saying that a is a multiple of b, if there is a whole number q such that we can write a as being equal to q times b. Right? So again, if you think about this statement, it's equivalent to saying that if I perform the Euclidean division of a by b, the remainder is 0. So this is an if and only if condition. And I introduced this notation here. We might use it, but we might not use it that often. Right? And once you introduce the notion of an integer being divisible by another one, then this would lead you naturally to the notion of a greatest common divisor. And so what is the greatest common divisor between a and b? And at least if you want to define this notion, then you have to assume that at least one of them is non-zero. Otherwise, this will not make sense. And so in that case, you define the greatest common divisor in the most natural way possible by saying that you look at the largest positive integer which divide both a and b. And you call this the greatest common divisor, and the notation is GCD. Right. So let's go back to our, before going back, I want to say that again, there is an algorithm by Euclid which shows that if you are given two numbers, a and b, again, the assumption is that at least one of them should be non-zero. This algorithm will it will return the GCD. And not only it will return the GCD, you can find two integers u and v such that you can express your GCD as u times a plus v times b. Right? And so if you go back to our running example, which was 93 divided by 33, we want to find the greatest common divisor of these two. So I'm guessing most of you have done this kind of calculation before. Do you know how to compute the GCD of two numbers? Don't be shy. Yeah, I see a lot of nodding. Yeah, so what we do, we do what you did in class. So we start by so we already made the first division. We got that 93 was 2 times 33 plus 27. And then we take 33 and then we divide by 27, and then we get this. And then now we take 27 and 6 and we divide, we get 3. And then when we take 6 and 3 and we divide, we get 0. So this means now we have to stop. And then, so we cross out this line. And then this is our GCD. So that's basically the Euclid algorithm in a nutshell. Right? And so now I told you the second part of the algorithm is that if you want, you can express your GCD as a combination of A and B by finding U and V. And again, the way you do this, so so basically here is nothing is lost. After you've done this hard work, you can use it to try and recover the GCD in terms of A and B. And the way you do this is as follows. So we are going to start at the bottom. I mean, there are various ways of doing this. So we start with this line. We can express 3 in terms of 6 and 27. And what that means is that 3 is now equal to 27 minus 4 times 6. So to do that, we use this equation. And then now we cross this equation out and we move to this one. In this equation, we have 6. Now we can express 6 in terms of 27 and 33. And so when we do that, that gives us the second substitution here. We arrange everything, then we get 5 times 27 minus 4 times 33. And then now we are at the last equality, so now we express 27 in terms of 33 and 93. And then when we do that and we make the corresponding substitution, we get this. So now we can say that our GCD, which is 3, is 5 times 93 minus 14 times 33, right? So again, it's one of those, I mean, it's a very simple algorithm. And if you think about it, it's an algorithm which was invented like thousands of years ago. But it's still one of the most elegant and efficient algorithms that I think if you're doing number theory or mathematics. So I think it's a very nice thing. And so once you've explored this notion GCD, then the natural question to ask is, are there numbers are there numbers that do not divide any other number other than themselves and 1, right? Which leads you naturally to the notion of prime numbers. And so in that case, what is a prime number? So in this case, you would say that a prime number is a number which is bigger than 1. And its only divisor would be 1 and itself, right? Again, we are going to see that this is also a very important concept if you do number theory. And you might not suspect this, but you come across prime numbers in your everyday life. We are going to see very soon. So does anyone have a favorite prime in the audience? Anyone? Yes? 2. Yeah. You? 101. 101. Okay. You? Yeah. So I yes. 17. Okay. Yes. 7. Yeah. Lucky 7. So I mean okay. It's nice to hear. You see, I'm pretty sure that each of you has their own reason of choosing that as their favorite prime, right? Okay, now the second question is, what is the largest prime that you know? I think your colleague is the one who said the largest prime probably in this list. Does anyone know what is the largest prime you know of? Yeah? Okay, we are going to come back to that question a bit later. You will see why I asked you that question. But you see, the next thing that you want to understand about prime numbers is that, fortunately, we have infinitely many of them. So it means that if you had to spend the rest of your life counting those prime, you would never get to the end, right? Because if you find 1, then the next thing you know, you would find 1 that is bigger, and then you keep going, and you keep going, and you keep going. And the other thing that we like about prime numbers is that, I guess it's kind of apropos that Alex went before me. So you can think of prime numbers as what atoms are to physics or maybe molecules are to chemistry, in the sense that if I give you a whole number, you can always break down into small pieces, and those small pieces are prime numbers, right? So to kind of illustrate this, if you look at 126, we can divide it by 2. the favorite prime of your colleague. And when we divide that, we can see that the number that we get would be divisible by 3. So we divide out by 3. And then we will see that the number we get is still divisible by 3. So we repeat that. And then when we do that, we will see that we are left with 7. So what that means is that I can write 126 as the product of 2 times 3 times 3 times 7. And if you want to rewrite that in some kind of elegant way, then you can say 2 times 3 squared times 7. So now the next question is, why do we care about prime numbers, right? And so to answer this question, I'm going to give you 2 answers. One of them will be kind of for practical reasons. And the second one, I would call this a kind of philosophical one, right? So, but before I do that, I'm going to ask you a question. I mean, I know that all of you are teenagers in this room, so it's a delicate situation, but I'm going to ask you, how many of you have a social media account? I mean, like, okay, you see, all of you, right? So maybe you have a teenage Instagram account. You have Instagram is owned by Meta. You probably use WhatsApp several times to exchange with your friends today. And then maybe you posted some silly videos on TikTok for your friend to laugh about, you see? And so if you've done all of this today, it means that in one way or another, you had to deal with prime numbers. So you see, whether you like it or not, you cannot avoid prime numbers. So that's why I said the reason why you cannot avoid prime numbers is the following. You see, all those text messages that you send to your colleague, think about it. Many of your other friends are doing it, so millions of people are exchanging data on a daily basis over the internet. So that's a huge volume of data. And the thing that you don't realize when you're doing that is that this data is sent through what we call open non-secure channels, right? So in principle, when you send your data, everyone can see that data. And so the reason why they cannot read it is that there are people who spend their time working really hard to protect that data and make it accessible only to you and your friend, right? And so that's why, even though your data is there for everyone else to see, it's protected, and then only your friend, who is the interested party, can read it, right? And the area of mathematics that deal with this is what some people call it cryptography. It's also called cryptology, right? And so when I said that one way or another you cannot avoid prime numbers, even if you want to, is that basically all the crypto system, I mean, when you send message on your WhatsApp, the crypto system that WhatsApp uses, it's based on numbers, right? So, and the principle behind is very simple. It's basically saying that if I give you a big number, being able to factor this big number is really, really hard. That's the principle behind all the crypto system. So in other words, finding a big prime number is something which is extremely hard, right? And think about it, people have been studying prime numbers thousands of years, right? As we saw earlier, all those statements about factorization and things like that, they date back to Euclid, right? So that's the practical aspect, the practical way of answering this question. And now, if you want to give a more philosophical answer, then there is this famous British mountaineer. They ask him, why do you want to climb Mount Everest? And then he said, because it's right there, right? So I'm going to give you an answer which is akin to that. So if you are a number theorist, you might just say, yeah, prime numbers, they are very beautiful objects. They have a lot of hidden pattern, and that's why I like them. So sometimes you study things, just because they are beautiful objects. See? So that's the philosophical answer to this question. Okay, so what we are going to do next, we are going to continue our exploration. And the next thing that we want to do, I call it modular arithmetic. So I'm not going to give you a very precise definition, but you're going to see that, hopefully you're going to see that it's a fun topic. Okay, so here I'm going to start with, by giving you some tables. So basically, we are going to assume for the next few minutes, I know it's going to be hard for the first time, but so what we are going to do, we are going to assume that we only have 7 integers. And then, so we want to perform addition using only those 7 integers. Right. So, and how we do this, it's basically what I explained to you in this table. So, but I'm going to explain to you how I got the table. So basically what the table does is very simple. Let's say if I take 1 and 2, and then I add them, I get 3, right? So 3 is smaller than 7, so I keep 3. I say 1 plus 2 is equal to 3, right? But what if I take 3 and then 6? 3 plus 6 is 9. 9 is bigger than 7, but we can only go from 0 to 7. So what I do, I divide 9 by 7. The remainder is 2. So I say 6 plus 9 is 2. So that's how I get the addition table. And the multiplication table, I do exactly the same thing, except I replace addition by multiplication. So for example, now if I take 3 and 6, 3 times 6 is 18. 18 is bigger than 7, so I divide 18. What is the remainder of 18 divided by 7? It's 4. Yeah. So that's the multiplication table. So for the next few minutes, we are going to assume that that's the only set of integers that we have, and then we're going to work with it. And now, here comes a fun question. So here is a picture of Rosalind Franklin with a microscope. So maybe some of you saw a picture when you walked in here. So she was a scientist here at King's, and she was actually very instrumental in the discovery of the helix structure of the DNA. Right. So that probably some of the stuff she was observing on that microscope. And so we know that Rosalind was born on 20th of July, 1920. So now what we are going to answer is the question, if I tell you that 20th of July this year is going to be a Sunday, then the question is, on what day of the week was Rosalind born? So does anyone know how to answer this question? Anyone? Yes? It's a Tuesday, yes. So how did you find it? You guessed. Okay, but your guess is correct. Okay, so we are going to see how to guess the correct answer, or how to find the correct answer. So the first approach is a bit naive, right? So the first approach, we basically count the days since she was born, right? So then how do we count the day she was born? Then she was born on, so what I'm going to do, I'm going to go from 20th of July, 1920 to 19th of July, 2025, right? So when you say you guess, you didn't look at in one of those websites where the day of the, no, okay, yeah. Okay, yeah, I mean, we're going to, but they probably use something similar anyway. So if you, then what that means is that it means that there's exactly 105 years since she was born, right? And then now, of course, among those 105 years, how many of them were leap years, right? So the number of leap years, because I can write 105 as 4 times 26 plus 1, I know that the number of leap years is 26. So that means that if I want to count the number of days since she was born, I take 105 times 365, and then I add the number of leap years, because those are the number of extra days that I have to add. And then what I get is that the number of days since Rosalind was born, as of 19th of July 2025, would be 38,351, right? And then now I want to ask myself, how many weeks was there since she was born? And of course, we do this division. We do this, so we see that there are 5,478 weeks since she was born. More precisely, 5,478 weeks plus 5 days, right? And now, so basically what we do, now we can label the week, the days of the week, and then I'm going to start that. Suppose that my week starts on Sunday, and then Sunday I did 0, Monday is 1, Tuesday is 2, Wednesday is 3, Thursday is 4, Friday is 5, and Saturday is 6. So 5 here will correspond to 5 here, which is Friday. But because we are counting backward, then we take the number which added to 5 gives 0. So in that case, it's 2. And so we know that Rosalind was born on a Tuesday. So so you can do it this way. If you have enough intuition, you can guess the answer as your friend just did. Or you can actually look this on the website if you want, because there are some websites where what day of the year was it? If you type in your thing, then it will give you this answer. Okay, so this is the first approach. So the second approach is that, you see, we only care about the remainder in this case. We don't care about the total numbers of days she lived. The question is what day of the week she was born in, right? And so what that means is that we only care about the remainder. So what that means is I can start by looking the number of days that we have in a year, and then see what is the remainder of this module when I divide by 7. That remainder will be 1. The remainder of the number of years since she was born is 105. When you divide that by 7, you would get 0. I didn't know this when I chose this example. I chose it because I like the history of Rosalind, right, as a scientist. And now the number of leap years, when we divide by 7, then we get 5, right? And now what we need to do to find the year in which, the day on which she was born, is to use this multiplication table that we saw, right? So now I only care about the remainder. So I take 0 times 1 plus 5, and in this case we are lucky. 5 is already smaller than 7. So that's 5, and you see it's exactly the same 5 that we found here, without computing the total number of years that she lived or the total number of days. And then now we do the same thing here, and we see that she was born on a Tuesday, right? So modular arithmetic is a very useful and power tool that you can use, right? And modular arithmetic, I mean, it's attributed to Gauss, who was a German mathematician. So basically what I explained with 7 at the beginning, you can do the same for any prime, right? So if you have a prime, then you look at all the numbers between 0 and p minus 1. And then you have this rule of adding them. So if a plus b is bigger than my prime, I divide and then I take the remainder. And I declare that to be my sum. And for the product, you do exactly the same. And this will give you a multiplication table and an addition table, as we saw with 7, right? And you see, this might not seem like it's true because, I mean, we are working with remainders. But if you were to study mathematics a bit further, or more specifically, if you were to study number theory, you would see that this is a very important tool, right? So this is what we call modular arithmetic. So I didn't want to give you a precise definition, but the intuitive definition is what I just gave you in the table with 7. So this is called modular arithmetic, and as I said, it's a very important tool, right? Again, I might sound like a broken record, but your WhatsApp application use modular arithmetic when you're sending messages. And the most surprising thing that I might say to you regarding this modular arithmetic is that you can solve equation the same way you do it with the integers or with the rational. You can do that. And even more surprising, sometimes if you start by solving an equation, let's say you have an equation with integers, you're looking for integer solution. Sometimes it might be easier to start by looking at whether you can solve that equation modulo some primes and use that to deduce that you can find solution for the integers. Or sometimes this can rule out very easily whether you have solution or not. So it's a very powerful tool, both from a theoretical point of view and also from a practical point of view, because we use it on the daily life when we do crypto. Okay. So now we are going to continue a bit of modular arithmetic. And here we are going to see, again, one of the things that I like is that you can do, one of the fun things when you do number theory that you can actually do a lot of experimentation. So I mentioned Euclid algorithm, which is some 1,000 years old. Now I'm going to tell you about one algorithm which I call Fermat-Little theorem, which is also a kind of fun algorithm to explore. So I'm actually going to ask you to help me solve this exercise a bit later. But here is what the algorithm does. I give myself a prime p, and then I choose an integer between 1 and p minus 1. And then what I want to find the smallest integer e, such that when I raise a to the power e and then I subtract 1, I get something which is divisible by p. And so the way I do this algorithmically, I start by setting b to be 1, and then I start a loop, right? So when for I equal 1, I set b to be b times a. If b is equal to 1, I stop. If not, it's happened that I reach p minus 1, I will stop. If not, then I multiply b again by a, and then I keep going, right, until I reach the p minus 1. And then I set my e to be I, and then I return e, and b mod the remainder of a to the e divided by p, right? So if you were to apply this algorithm to in the case of 7, what do you expect the solution to be? So I already wrote what it will be for 1, so I'm going to divide you in 6 groups. So I want you to take 2, and then you see if you can do the calculation mentally for 2 and see how many steps you need and what is the final answer. The second group, I want you to try 3. So how many steps do you need, and what is the final answer? The third group, I want you to do 4. The 5th group, I want you to do 5, and the last group, I want you to do 6. And then so I'll give you 1 or 2 minutes, and then tell me what you got as a. Okay. So did you? Okay. Did anyone manage to finish the calculation? Yes. 3, and then for 4, you mean? Yeah. That's okay. So and then what's the answer? You said 3. Oh yeah. Sorry. So you got 1. So you mean the final answer is 1, and you had for E you got 3. What? Who else did? What did you find? For 2? 1, yes. 3 step. And 5? How many? Okay, so we're going. So for yeah, so okay, so if you look at 3, so 3 to the cube is 20, right? 3 to the cube is 27, and what is 27 mod? What 27 mod 7? It's 6, right? And then if you take 6 times, so I said 3. No. What? So 3. So yeah, sorry. I said 3 to the cube is 27, and modulo. Yeah. What did I do? I think I mixed up my calculation now. Yeah. If we multiply by 6, sorry. So that's 36, right? And what is 36? Then that's 35 plus 1. Right? So for 3 we get that we have 6. Right? And then for 5, for 6, then what do we have? So 6 should be 2. And so if you look at this calculation, yeah, sorry. Did you notice anything about E here? E, you see, E is always a divisor of 6, which is 7 minus 1. And this is not a coincidence. It's not a coincidence. Every time you do and what I'm going to show you next is that this is actually true for any prime number that you can find. So and this is what we call the Fermat-Little theorem. So the reason why I call this algorithm Fermat-Little algorithm, because Fermat didn't call it that way. I gave it that name. But it's because of this result. So what we did there, it's true for any prime number. So if I give you any prime number and you choose a number between, if you choose a number between 1, or if it's 0, between 0 and p minus 1, then this difference would always be divisible by, p. And if you exclude 0, then this, because if you exclude 0, then now this will always be divisible by p. And not only that, the smallest power of where a to the e minus 1 is divisible by p, this will always be a divisor of p minus 1. So this phenomenon that we observe for 7, it's true for every prime number. And it's one of those very striking properties about prime numbers that you can find, right? And so a number which satisfies this kind of property, we call them a Fermat-like prime, a Fermat-like number, sorry, right? We know that prime numbers satisfy this property, right? And so now the question is, are there any other natural number which share this property, right? And in this case, the answer is actually yes, right? So, and if you think about this question, it could be a question as asking, are there numbers that kind of camouflage themselves as Fermat, as prime numbers, in the sense that they have this same property, which is the Fermat properties for numbers, right? And so that's, before I go any further, I want to, can you see the snow leopard in this picture? Can anyone see? You see, it's hiding very well, right, in the mountain. Anyone see? You see, you're taking quite a few seconds to spot it, and you can't find it. You see? Huh? Has anyone found it yet? Okay. If you look at here, oh, you see it here. Can you see now? Okay, so you see, and I mean, so you see, so animals have this capacity of hiding among in nature, right? But we know that they do it with a purpose, right? But I mean, we cannot say the same thing for numbers, right? I mean, so here, what is the fake prime in this list? What is the fake prime in this list? Okay, I think you will spend a lot of time staring at it, but let me tell you it's here. You see, so you can see that it's divisible by 3, right? The digit add up to 2. Okay. So, and the reason I call it fake prime is because it's a Fermat-like number. So if I were to, this test that we apply, this algorithm that we did, if you use that algorithm, this would behave like a prime number. But it's not, because you see we can factor it as 3 times 11 times 17. Right? And these numbers, they are what we call, of course, I already used the term Fermat-like number, but some people also call them Carmichael numbers. And I mean, I guess it depends what way you see it. You can see that if I tell you that we have infinitely many of these numbers, you might think it's a good thing, or you might think it's a bad thing, right? But for me, it's a good thing, because if we didn't have this, then it would be too easy to determine when a number is a Fermat prime, and a lot of people would be out of work, right? We don't want that. So then this begs, so we know that if we were interested in looking at numbers using these Fermat properties, we would have a lot of numbers that would behave like prime numbers, but in fact they are not. And what I want to say is that, I mean, so I just told you that we only have, we have infinitely many of them. So these are the first 7 Carmichael or Fermat-like numbers that you have. You see, so the first one is this, which tell you that they are kind of very rare, because you see the first one is quite big. The first prime, which is the favorite prime of your colleague, is 2, right? But we have to go to 561 to find the first Carmichael number. So they are rare, but they are still infinite, I mean. We cannot call them quite diamond, even though they are rare, but still, right? And so this Fermat-like property that I mentioned, it's one way in which prime numbers can hide, not prime numbers, but other numbers can camouflage themselves as prime numbers. So this kind of raises the question, how do we find, if I give you a number, how do you determine that number is a prime number? Or if I give you a big number, how do you factor it into prime? Right? And the answer to this question is people use primality tests. So we are not going to go into too many detail about this, but primality testing, there are 2 kinds of primality testing. The one that are deterministic and the one that are probabilistic. So the deterministic one, as the name suggests, it tells you for sure this is a prime number or it's not a prime number. The probabilistic one, it tells you maybe 99.9999999, this is a prime number, but I cannot tell you for sure that it's a prime number. Right? So there are plenty of tests. And so one of the things that the people there are people working behind the scene to come up with good prime, big prime, that are used by the people who are working on your WhatsApp application. And one of the favorite tests that they use in that case to check for prime is the Rabin-Miller test, right? So I'm not going to give you the full strength of the Rabin-Miller test, but I'm going to show you something that you already can see, because it uses things that you know. You see, the identity that I'm using here is that I can write this as a minus 1 times a plus 1. And this gives you a very simple criterion to determine whether a number, whether two numbers share the same GCD, right? And in this case, I give you a number n, which in this case I'm going to assume is odd. And then I give you another integer n, which is bigger than 1. And then it says that if we have these two conditions, first I know that n would divide a squared minus 1. And then I know that n doesn't divide a minus 1, and n doesn't divide a plus 1. If that's the case, then I know that a minus 1 and n would have a GCD which is bigger than 1. So this is essentially the content of the... So for the Miller test, you basically crank this up, and then you get a primality test. So it's a very... So again, if you apply that to our running example, to our fake prime, if you apply this and you take a to be 67, you see, if you take a squared minus 1, you can check that this is 4,488, which you can write as a times 561. And so in this case, and then you can check that a minus 1 is 66, which doesn't divide 561. And then you can check that a plus 1 is 68, which again doesn't divide 561. And so this theorem tells us that the greatest common divisor between a minus 1 and n, which is the greatest common divisor between 66 and 561, is bigger than 1. In other words, 561 cannot be a prime, right? And in this case, you can actually compute that the GCD is 33. Right? So there are plenty of tests like this, but the Rabin test is really a crank-up version of this, and it's the most used test because it's the most efficient test, basically. And so what I want to say is that, so you have to beware of old saying, which says, walk like a dog, talk like a dog, quack like a dog. It's probably a dog. Now I'm going to finish with a question that I asked you earlier, which is, what is the biggest prime that you know? Anyone? What is the biggest prime that you know? Yes? Yeah, that's a good answer. Now you know that this is the biggest prime that we know to date. So this one was discovered only on October last year. So it's fairly recent. And so it has 41 million plus digits. And this type of prime, they are called Mersenne primes. Fortunately, to do crypto, we don't need primes that are this big. Most of the crypto system, they use prime with about 600 decimal digits. Back in the 70s, they only need 20, 50 digits. So you see, the more the computer gets powerful, the more we need the prime to be bigger. And how many pages do you think we would need in order to print this number? How many pages? Any idea? 65,000. Yeah, you? Never mind. I didn't say it was correct. I was just... I was going to say like 683,000. Who else? Yes? No. Okay, yes, he's very optimistic. Yes, you? 103 pages? No. Yes? No, I mean standard book. Yes?
3,000,
Okay, I mean, yeah.
136,748.
Yeah, that's very precise. How did you find that? Yeah, I mean, yeah, I think, yeah, probably in the, so I was actually going to do a live demonstration, but my laptop wasn't working. But I did a demonstration with the previous number, and it was about 10,000 pages, right? And this one is much bigger. So you might get something in the range of maybe 20 to 30,000 pages. But unfortunately, my laptop couldn't do this. So, I mean, but yeah, so I think this is a good place to stop. Thank you very much.